Okay, so let's continue. So I would like to summarize this off policy like divergence issue that we have. Okay, so now as I mentioned before, like so we have three components which when combined like is going to be a problem. Like we're going to call these components as the deadly triad. Okay, so you have function approximator and you have bootstrapping. Okay, and you have off policy learning. Okay, so whenever you combine all these three components, you will face instabilities. Now, this is not well explored in the literature. Okay, so this is still an active research area, like so on like what are the reasons for this and like how to resolve this and so on. But one thing that is clear, like at least based on our examples, is this instability is not because of the control problem or the generalized policy iteration. Okay, we see these instabilities even in simple prediction problem. Like the examples that we have seen so far are prediction. They are not controlled. We don't use policy iteration there, right? So now, even for simple prediction problems, we have instabilities, right? Now, which means this danger is not due to learning or uncertainties about the environment. Okay, so because it also happens in DP. So in DP, you're not doing any learning. You're just estimating. You have access to the environment, right? Like so, even when you have access to the environment, when you're not learning, you're just estimating, you have these instabilities. Okay, now we can kind of summarize all the class of algorithms we have seen so far in one table. Okay, so in one side we have on policy or off policy. Okay, then we have some algorithms, and for each algorithm we have the tabular version, we have the linear function approximation version, and non-linear function approximation version. Right now, there are two major classes, like either on policy or off policy. So in on policy, you can either do Monte Carlo or TD. Similarly, in off policy, you can do Monte Carlo or TD. Okay. Now, Monte Carlo methods are simple. Okay, and there is no bootstrapping involved. You can prove that they converge in all the tabular linear function approximation and nonlinear methods. Okay, so they are simple. Now, when you think about on policy TD, so on policy TD function approximation, like so tabular, all the methods always converge, no issues. Okay, now when you do linear function approximation with TD, okay, you have two components out of three. Okay, so in that case, for linear function approximation, we know that it converges, but we don't have any convergence guarantees for nonlinear function approximation. Okay, however, when you are in off policy world, even linear function approximation doesn't converge. Is that clear? Now, if any of these two out of three components are present, then instability can be avoided. Okay, so now let's talk about all these three components. Okay, for a moment. So first we have function approximator. So can we remove function approximator? Is it a good idea to remove function approximator? Definitely not, right? Like so, if you want to scale up to complex problems, you can never scale up without function approximator. So it is one of an essential component, so we cannot remove it. Okay. Now what about bootstrapping? Depends on the problem, yes. So what are the advantages of bootstrapping? You can do it, basically you learn faster. So there is both computational efficiency because you don't need to wait, and also data efficiency. Okay, so we have seen through some experiments that bootstrapping methods like TD learn faster than Monte Carlo methods. Okay, so they have some advantages. Okay, however, like if you avoid bootstrapping, like you have issues like, for example, you cannot do continuing tasks anymore. Even for normal discounted episodic, even for episodic tasks, like if you don't have bootstrapping, then you're going to have very slow learning, which is okay for some cases, not okay for other cases. So it is a very difficult component to remove as well. Now, what about off-policy learning? Can we remove off-policy learning and always do on-policy learning? So are there situations where you would have to do off-policy learning? So at least based on our previous discussion, right? Like, so we know that if you do just on-policy learning, you can only learn epsilons of policies. You cannot learn greedy policies. Like, at least you cannot learn greedy policies unless you have exploring starts, which is a very unrealistic assumption. Like if you want to consider complex real world problems, right? Like, so there are situations where you cannot do on-policy learning, okay? Also in general, if you think about how humans learn, right? So like my life, like in a day consists of several tasks, right? Like, so I learn about a lot of things, but my experience or my episode is just one, right? So I have some behavior policy, which is my behavior, right? However, I'm learning about things that I would not have done, like even things that I would not have done, like by just experiencing through the behavior policy, right? So this is a very abstract discussion, okay? So the point here is, if you want to learn about more than one thing, if you want to learn about many things, which is what is desirable from like an ideal AI system, right? Like, so we want a robot which is multi-purpose, like which can do cleaning the room, cooking food for you, doing the laundry, like talking to the guest, showing path and everything, right? Like entertaining your babies, right? Like, so if you want something which can do many tasks, right? It is very difficult to learn that with on-policy learning. Okay, so in those situations, you have to do off-policy learning because it is just easier, like to do these things with off-policy learning. So in some sense, it is very difficult to remove all these three components. Okay, so we have to live with these three components, which means we should develop algorithms which can be stable, like when you use all the three components. Okay, now so far I told a lot of. Okay, so there's a comment which says the exam calendar was just published. So for people who asked about exam, the exam is on December 13 at 1:30 p.m. So there was also another previous question about the nature of take home. So I don't want to commit right now, but like what I think we will most probably do is a limited time exam during the given exam hour. So if the exam hour is 1:30, probably we will do a 3-hour exam or 4-hour exam, like where, well, it's not more than 3 hours, but an extra hour to scan or typeset things, and you will be submitting it on time. Okay. The other option is to give you a 24-hour take-home exam, which is going to be more challenging than the 3-hour exam. So, like I will think about it. Probably it is easier you do the 3-hour exam than the 24-hour exam, given that you have other courses. Okay, so getting back to our deadly triad. So how do we resolve this issue, right? Like, so first of all, it is not very clear. Okay, first of all, I showed you a lot of counter examples, but how probable are these counter examples? Like, are you going to see these divergence all the time? So the good news is, if you use powerful function approximators, okay, so which goes back to the representation, right? Like, so like in all these cases, like I constructed the representation, but if you use really powerful function approximators, then the chances are that you will not diverge all the time, okay? However, you will still diverge once in a while. So it is not a completely solved issue. Okay. So, but what I want to highlight is like if you have powerful function approximators, then the chances of divergence is less. Okay. So we're going to see one such powerful algorithm. Okay. So which is deep Q networks. Okay. Now, or DQN. So DQN is basically just a combination of Q-learning and neural network function approximator. Okay. So we have Q-learning. Instead of having a linear function approximator, I'm just going to have a neural network function approximator. Okay. Now, we already know that when you do function approximation with Q-learning, we might diverge, right? Because Q-learning is an off-policy algorithm with bootstrapping, and you're using a nonlinear function approximator to make things worse, so you will diverge, right? So now, historically, people tried using neural networks with Q-learning, like the very first successful implementation of this was in 1991 or 92 by Jerry Tesoro from IBM, who developed a backgammon agent, like playing agent, which was probably one of the early success of AI, in the sense he developed a simple TD combined with neural network, okay, which was able to beat the human champion of backgammon in 91 or in early 90s, okay. So even the chess thing, the chess agent which won Gary Kasparov was after that, like I think it's 96 or 97. But the chess agent was not a learning agent. It was a huge search-based agent. However, this backgammon agent was a reinforcement learning agent, which learned to play the game from scratch by playing millions of games, and it was able to solve. Okay, but that was the only success story of combining neural networks with as a function approximation for reinforcement learning. Like after that, a lot of people just thought, okay, it's going to diverge, so it's not worth thinking about it. But after the success of deep learning, like in early or late 2000s, right? So then a group of researchers, like from DeepMind, which is now acquired by by Google, right? So they developed deep Q networks, which is basically the plain old neural network function approximation plus Q learning, which is exactly the same thing that Jerry Tesoro did in 1992, okay? But after 20 years or 22 years, so with the lessons that we learned from deep learning, these researchers added a bunch of tricks to stabilize this algorithm, okay? Now, these simple tricks helped them to make sure that this algorithm does not diverge. Now, what are these tricks, right? So there are two major tricks used in deep Q learning, which is different from the usual neural network function approximation for Q learning, okay? So the first trick is the idea of using experience replay. Okay, now what is experience replay? So in the case of DQN, okay, so the agent is going to store all the historical transitions in a buffer. Okay, we are going to call this as replay buffer. Okay, so every transition in the episode that it is seeing, like a transition is basically state, action, reward, next state. Okay, so you store all the transitions that you have seen so far in this replay buffer. Okay, now when you do Q learning update, instead of considering the current experience to do your update, you are going to sample a mini batch of transitions. Like for example, let's say my buffer has a million transitions. I'm going to randomly pick 10 transitions and do updates using these 10 transitions. Is that clear? Now, first of all, why is this a good idea? So there are many advantages.
The replay buffer, is it a bunch of entire episodes or just one action that happens?
Well, it is just a bunch of transitions. Okay, we are talking about one-step Q learning. So like you only need the transition, right? Like state to next step. But of course, if you do n-step Q learning, then probably you need like a transition, like a chunk of the episode. You would be storing chunks of episode. But for one-step Q learning, like you just need a transition. Now there are several advantages for doing this. Okay, so first of all, we have data efficiency, right? So we are storing these examples instead of throwing them away. I'm repeating these examples again and again, which means I can be more data efficient. Okay. And second of all, picking this random bunch of examples, right? It breaks correlations. Okay. And hence reduces the variance in update. Okay. When you make your updates directly on the trajectory, the next state is correlated to the first state. Like there's a lot of strong correlations in the episode, right? So you can easily construct situations where like you will get into loops or you will get into like high variant updates, like which all leads to instabilities. Okay, now that is avoided. Okay, and finally, by using the replay buffer, you are averaging the behavior distribution. Right? So you are using samples of transitions even from the past, right? Which means you have this average behavior which could avoid oscillations or divergence. Okay, so there are many benefits in this one simple trick, which is basically to use a replay buffer and do your updates based on the replay buffer, not based on your current episode. Okay. Now, in practice, when you implement DQN, like so, you will not have infinite buffer. So you will have a limited buffer, and you will just store them one by one. When the buffer gets filled, you flush out from the past. So it's like a first in, first out buffer. Is that clear? Now this is the first trick. Okay. Now what is the second trick? So the second trick used in DQN is the idea of target network. Okay. Now, usually we have a neural network function approximator, right? So now if you think about the TD error for Q learning, right? Like so it's going to basically del T is equal to RT plus 1 plus gamma times max over A Q of ST plus 1 A given my parameter of the neural network theta times T minus Q of ST AT given theta T. Is that right? Now, you can see that one of the reasons for this instability is the fact that I'm using the same neural network that I'm updating to also to compute my target, right? Now this part is the target, RT plus 1 plus gamma times max over Q. Now the target has the same theta, which means every time theta changes, my target also changes, okay? Now it was kind of okay in linear setting because things move slowly, but with non-linear function approximators, you make a small change to theta, things can move like far away, okay? So the interactions are non-linear here, right? Like so, like you're going to have a huge non-stationarity, like if you have this issue, like if you have this coupling, okay? The simple idea that DQN has is to kind of decouple these two things, okay? Instead of computing my target with the current parameter theta t, I'm going to compute it with theta t minus, okay? Now this theta t minus is a separate neural network, okay? So I have my current network, which has theta, and I have my target network, which is represented by theta minus, okay? Now, for every k steps, I'm going to copy my current network to the target network. Is that clear? So it is going to look some like my theta minus is going to stay same for k steps. Then I'm going to make some updates. So maybe it is here, and I'm going to make some updates. Okay. So even though the target is moving non-stationarily, for a limited period of time, my target appears to be stationary. Now this is really crucial because it helps you to avoid a lot of instabilities. Okay. Now you remove either of these two tricks, like you'll have a lot of instabilities. Okay. Yeah.
I think I remember you did something similar when you were trying to avoid that max bias.
Oh, okay. So yeah. So So for maximization bias, we had the concept of double Q learning, right? But it is not same as this. So if you think about it, like so double DQ, like so double Q learning is just based on this. Like so you're using the same Q network for max as well as estimate, right? So you will take max, like so here you'll have two different Q values. So in fact, this is orthogonal to double Q learning. So you can combine DQN with double Q learning, you get double DQN. So it's not the same. The target network here is not same as the double Q learning second Q network. Is that clear? Okay, so now apart from these two tricks, there is also another third trick which people often forget, which is really the idea of reward clipping. Okay, now things diverge because you have huge updates, right? So especially when you have like high reward, like high variance in reward, like so sometimes you get a reward of 1, sometimes you get a reward of 100, sometimes you get a reward of 1,000. Okay, now things can easily diverge, like because the updates become so huge. Okay, to avoid this issue, so they clipped all the rewards from -1 to 1. So anything above 1 is clipped to 1. Anything below -1 is clipped to -1. Okay. Now these three things put together was able, like they were able to come up with a really stable algorithm, like which can solve really complex tasks. Okay. Now when you combine this with deep neural networks, like some of the networks that we have seen in the beginning of this lecture, you can solve really complex tasks. So here is an example. Like so, in this case, like the first success of DQN was in playing Atari. So several of you might have played these arcade games, right? Like so there is Breakout, Pong, Asterisk, and a bunch of other things here. Like so, there are like I think 50 or 55, 50 to 60 games available in this suite of Atari learning environment. Now, pre-DQN, it used to be really challenging task for reinforcement learning agents, okay? Because your observation here is this image. Now, given this image, you need a good representation of this image so that you can use your reinforcement learning algorithms on the top, okay? Now, the way in which they were able to make it work in DQN is by using convolutional neural networks, okay? So you take the image, you pass it through the convolutional network, okay, sorry. You pass it through the convolutional network, okay, and followed by one linear function approximation. Okay, now there is also another nice trick here, which is we are interested in estimating Q of S comma A, right? Now, instead of trying to pass state with many possible actions to the network, they only pass the state to the network, and they try to estimate the Q value for all the actions in parallel. So this is Q of S comma A1, this is Q of S comma A2, and I think there are like 18 possible actions in Atari. So you estimate all the Q values in one shot, and then like you have your Q value estimation. Is that clear? Now, so here are some results. Okay, so here you can see that here you see a comparison of deep Q network with the best possible linear function approximator available at that time. Okay, so now you can see that the gray lines are linear function approximator, and the blue are the DQN. And here you see that above this line, like the scores that the agent achieves are above human level. Okay, well, so what is the human level is very questionable. Okay, so probably this is not, you should not take it for like as such, like so, like it really depends on which human like you are comparing this agent with. So best possible players might have like really great scores in this, right? Like so, this is basically some average human team, like a bunch of average humans like who played the game, and like the agent is on par with them or much better than them. Is that clear? I want to show a video of this agent, but I forgot to take it out. So just give me 1 second. Okay, so probably, yeah. Yeah. I think in this case, we don't need the audio. So here you can see DQN in action. Like, so this is after 10 minutes of training. So you can see that it is trying to hit the ball. Sometimes it misses. Okay. Now this is after 120 minutes of training. You can see that it is already doing very well. So this is after 240 minutes. Like so now you can see that this network or DQN has figured out like a trick that humans often figure out, which is basically you just hit one side of the thing. So now you can just go to the top, and then you can hit all the things for free, right? So this is one of the good performance example. Like, but there are also a lot of other bad performance examples. Like, I don't have them with me, but the point is, like, this is one of the earlier like success of like what people call as deep reinforcement learning, which is basically the idea of taking all the reinforcement learning algorithms that we have seen so far and combining it with deep neural networks. Okay, so but the combination is not that trivial. As you can see, for doing combination of Q learning with deep learning, like we had to do some tricks. Similar things would be there for all the other learning algorithms. Okay, so so this week's reading, I think I did not give reading for quite some time. So this week's reading are a couple of papers. Like, one is the original DQN paper. So now you are all equipped to read the paper. You should be able to understand it, and which also means you can read most of the deep reinforcement learning papers now. With the theory that you know. So it helps you to choose papers for your project. And the second paper, like for reading, is about connections between deep reinforcement learning and daily triad. Okay, so they're both interesting papers to read. Okay, so I think that concludes our discussion on function approximation and off-policy function approximation specifically. Okay, so now I want to take, I think this is the right time for me to introduce a third class of problems. Okay, so far, if you think about it, like we can handle two types of problems. So the first is episodic, right? If things terminate, then things are easy to solve, so we can handle it. Then the second class of problems that we had is continuing problems, right? In continuing tasks, episode never ends. Like, so for example, a robot which is supposed to clean the campus. So it tasks never ends, right? It's always cleaning, right? So there are a lot of like controlling things in a power plant, right? Like, it's a continuing task. There's no end, right? Like, so there are a lot of continuing tasks. And we also discussed in the very beginning, probably in the second or third lecture, that when you have continuing tasks, right? Like, so you need or you must use a discounting factor gamma, right? So continuing task discounted. So can someone tell me why? Why do I need discount factor in continuing tasks? Someone else? I want someone who has not answered so far. People in the chat can also answer. I'm going to answer the questions in chat soon, but after this. So why do we need discounting factor in continuing tasks? What happens if you don't have discounting factor? Yeah?
Otherwise, keep adding rewards and we go to infinity.
Yes. So then you have this infinite return, right? So there is like you cannot maximize the infinite return. Okay. But if you remember, when I talked about discount factors, I also told you that we can actually do undiscounted continuing tasks, but for future, right? Like that is what we are going to see today. So we can actually, we are going to see a new formulation, which is undiscounted continuing tasks, okay? Now we're going to consider continuing tasks. Okay, I think, I hope I can, just give me 1 second. Okay, so we're going to consider continuing tasks, okay, but without discounting. Okay, now when you don't have discounting, like how do we handle this sum being infinite, right? So one simple answer for that, so let me see if I can use my pencil. I really need to buy 2 pencils. Okay, so one simple answer for that is the idea of average reward setting. Okay, so instead of considering the sum of rewards, okay, what if I consider average of all the rewards? So this can be controlled and not go to infinity. Okay, now first of all, let us define what is average rate of the reward. So we're going to call that as R pi. R pi is the average reward that you get by following the policy. Okay, so this is basically limit h tending to infinity 1 over h, summation time is equal to 1 to h, expected value of RT given as 0 and all the actions that you have taken so far from the policy. Is that clear? Like you consider expected return from each time step and you average all of this over this infinite sequence. Okay. Now you can approximate this as limit h tending to infinity, sorry, limit t tending to infinity. Okay, expected value of RT given as 0 is 0 t minus 1. Okay, now I can expand this expectation now. So this is basically summation over all possible states. Okay, the probability of visiting this state in long run. Okay, so not now, like in long run, the probability of visiting this place, we're going to introduce this new thing, mu pi of s. Okay, summation over all possible actions from the state, summation over all possible next states and reward, probability of s dash r given as a r. So this whole thing is the expectation. So this is the expected reward. Is that clear? Is that clear? Now what is this mu pi of s? This mu pi of s is the steady state distribution. Okay, now, so what is steady state distribution? This is the distribution of my MDP transition probabilities when time goes to infinity. Okay, so mu pi of s is basically limit t tending to infinity, probability that st is equal to s given a 0 to t minus 1. Okay, now, the idea, okay, so the steady state distribution basically means that after a long time, my transition probabilities are going to converge to just one probability distribution. Okay, so what does this mean? This means that I can start my MDP wherever I want. I can take whatever action I want. Okay, my initial state and initial actions does not matter in long run. In long run, my transition matrix will reach a stage where when I transition from one state to another state, next state probability is exactly same. Okay, so if you know about like probabilistic processes, like so this is called ergodicity of the state of the process. Okay, so now we just assume that this MDP has this ergodic nature. Okay, so we are making this ergodic assumption. Okay, which is assumed to exist for any policy pi and independent of the initial state. Okay, now this ergodicity assumption is sufficient to guarantee that the limits for these infinite things, right, like that exist. Okay, but probably we will not get into that detail now. Like, but I just want to tell you what is the steady state distribution. The steady state distribution, as I mentioned before, is the situation where I am in a state, I transition, I go to the same next state probability. Okay, so summation over all possible yes, mu pi of yes, summation over all possible a, pi of a given yes, probability of s dash given s comma a, right? This is going to be simply mu pi of s dash. Okay, so in some sense, this is the fixed point for this distribution. Like so, like I transition again and again, like the distribution doesn't change. Okay, now with this assumption, now we are ready to extend all the algorithms that we have seen so far to average reward setting. Okay, now for example, return in average reward GT is defined as RT plus 1 minus R5, okay, plus RT plus 2 minus R5 plus RT plus 3 minus R5 and so on. Okay, so my return previously was just sum of all the rewards. Now it is sum of all the differential rewards. Okay, we are going to call this as differential return. Okay, because I take all the rewards, I subtract by the average and I sum that. Okay, so now we can see that this is contained, it's not going to infinity. Now we can also extend our Bellman equations to this setting. Okay, so all we have to do for that is we don't need gamma anymore. Okay, so you remove the gamma and instead of RT you have RT minus average reward. Simple. So for example, the state value Bellman equation V pi of s is equal to summation over a, pi of a given s, summation over r s dash, pi of s dash r given s comma a. Okay, or previously it used to be r plus gamma times value of next state, right? Now this is going to be r minus r pi plus there is no gamma, just v pi of s dash. Is that clear? Is that clear? Now similarly, I can write q pi. So q pi of s comma a is going to be summation over r s dash p of s dash r given as a. Okay. Previously it was r plus gamma times max q, right? Now this is going to be, sorry, not max q. In this case, like it's an update equation. So gamma times expected q, right? So now this is going to be r minus r pi times. There is no gamma, just summation over a dash, pi of a dash given s dash, q pi of s dash a. Okay. Now I can also write the Bellman optimality equation similarly. So the optimality equation for state value is given by max over a, summation over r s dash, probability of s dash r given as a. Okay. Now r minus max over pi r pi plus v star of s dash. You can see that there is no gamma here again. So similarly, I can write the q star of s comma a. This is summation over r s dash, p of s dash r given s comma a, r minus max pi r of pi plus max over a dash q star of s dash a dash. Okay. So we're essentially repeating all the traditional Bellman equations and Bellman optimality equations, but now we can write it in average reward rotation. Similarly, your TD errors can also be updated. So for example, del t is equal to RT plus 1 minus RT plus 1 bar plus V bar of ST plus 1 WT minus V bar of ST given WT. So this is when you have function approximation. When you have function approximation, so if you remember, this used to be RT plus 1 plus gamma times V of next state. Now we have RT plus 1 minus this R bar thing, which is basically my estimate of the average reward. So how would you estimate average reward in practice? It's just easy, right? Like you just compute the average, running average. Okay, so in whatever way you want. So you have an estimated average reward, then like plus the value without gamma, right? Now, similarly, you can also have the same thing for Q function. I'm not going to write it. Okay. So here is an example algorithm. Okay, I think I forgot to add the example algorithm. So just give me 1 second. How did I forget? Okay, that's the only thing I forgot. So good. Okay. Okay, so you can see here is an, I think it is, we need to wait for the camera to clear. So while the camera is clearing, like I can answer some of the questions in the chat. Does the architecture of the two neural networks must be same for target network? Yes. So the target network essentially has to be exactly same as the current network. Otherwise, how would you copy from one to other, right? So then there is another question. So how will reward flipping help instability? So like I think I explained this. Like so, when you do reward flipping, like you're also controlling the amount of TD updates. So you don't make big updates, which helps in removing them, like which helps in reducing the instability. Any other question? Yeah.
So the new Bellman equations and Oxford equations, I'm assuming they are also going to have the same guarantees about like unique solution.
Yeah.
So why do we want the undiscounted new setting numbers?
Why do we want the new setting?
Yes. What is the advantage of this?
Okay, we will come to that.
Okay.
So that is what I hope to finish today. So I will finish it hopefully. Okay. I really don't want to take small part of the next week. Okay. So here is an example algorithm. Like this is differential semi-gradient Sarsa. Okay. This is basically semi-gradient Sarsa, as you can see. So the only difference is the update here doesn't have gamma. Instead of gamma, they have R bar. Right? So that's the only difference. So now you can extend all the other algorithms like n-step Sarsa and things. Like I'm not going to do that, but the book has some more examples. But there was an interesting question, like why did I suddenly introduce this? Right? We were happy with discounted settings, like why undiscounted settings? So we'll come to that. So undiscounted settings make more sense in function approximation. Okay, so we're going to talk about depreciating discounted setting. Okay, so this continuing discounted problem formulation, right? Like it was useful in the tabular case, okay, but it is actually questionable in the approximation case. Okay, now I'll give you an example to motivate this. Okay, now consider an infinite sequence of returns, okay, with no beginning, no end. So that is my sequence. Okay, now the states are not clearly identified. Imagine you are always in one state, just to make things simpler, okay? Approximately all the states are same, okay? All the feature vectors are same, okay? Now, this means that state doesn't matter. What matters is just the reward sequence, right? Now, how would you estimate the value of the state? There is an infinite sequence of rewards, and in every time step, it is the same state. So how would you estimate the value of the state? Simple question. Yeah.
I don't see any issue with discounted return here also.
Oh, there is no issue in discounted return. That is true. But what is the simplest solution here?
Then just add on
The simplest solution is just take an average of all these, right? Like, because it is only one state, you're seeing an infinite stream of rewards from the state, right? So you just average this over a long interval, right? Now that is the idea of average reward setting. But we also have this alternate setting that we have discussed before, which is the idea of discounting, right? It is true that idea of discounting can be used here, okay? However, some returns are going to be small, some returns are going to be large, and you have this bunch of discounted returns all from the same state, right? Which means you're going to take an average of this discounted returns to estimate the value. Is that right? Right? So that is what we are doing, like when we have many visits for the same state, right? So now, it turns out that for this setting, the average of the discounted returns is proportional to the average reward. Okay. Now this is, why is this interesting? This is interesting because now I can now I can remove gamma. So gamma is a thing that we need to find the right value, right? So now I can actually remove gamma in this setting. Okay. So we're going to prove that. I really wish I had some extra time. So, okay, is it okay if we just go up to 225 today? Like, I really don't want to take this to next week. Okay, so it's a very simple proof, like, but let's do that. Okay, so now I can actually show you that if you do discounted return for this problem, then the solution that you're going to get is basically r pi by 1 minus gamma. So what does that mean? You can count, in one side, you have average return, average reward setting, but there is no gamma, you get the value r pi. And in other side, like you have discounted return setting, where the value is scaled by 1 minus gamma, but that doesn't really matter, right? Like, because this is the same scaling for all the policies. If I have to find the optimal policy, I could very well do that with r pi. I don't need to do r pi by 1 minus gamma, right? Now, this means that gamma has no effect on my problem formulation in these kind of settings. Okay, so let us verify that. So let us say this j pi is the average value that we are looking for. Okay, now this is given by summation over s mu pi of s v pi gamma of s. Okay, so usually we will call v pi of s for the value of the state. Given that we have discounted and undiscounted settings now, v pi gamma of s just means that it's the value discounted, value of the state computed using the discounted return. Okay, it's a discounted value function. Now, mu pi is the steady state distribution. Okay, so now I can expand this value. Okay, so summation over s mu pi of s, summation over a pi of a given s, summation over s dash r p of s dash r given s a, r plus gamma times v pi of s dash, right? This is what you would get in the traditional discounted return setting. Now, we know that this particular thing is r pi. It's the definition of r pi, right? So I'll take r pi out. So this becomes r pi plus summation over s mu pi of s, summation over a pi of a given s, summation over s dash r p of s dash r given s a, gamma times v pi gamma of s dash, right? I can take the gamma completely outside. It is not dependent on any of the states or action. So this becomes r pi plus gamma times, okay? If you think about this particular term, it only depends on s dash, right? It is not dependent on a or r, or even s for that matter, right? So I'm going to take it completely out. So summation over s dash v pi of gamma of s dash, and the rest as such. Summation over s v pi of s, summation over a pi of a given s, p of s dash given r comma a. Is that clear? Okay, we are almost there. So let me copy this. Okay, let me copy this to the next page. Okay, now this is r pi plus gamma times, okay, summation over s dash v pi gamma of s dash. Okay, now what is this? Remember that we are in this infinite sequence with steady state distribution. So this is basically the probability for the next state, right? So that is also mu pi. So this is basically mu pi of s dash, right? So now this is r pi plus gamma times. Now you see, what is this? This is just the definition for j pi, right? So j of pi. Is that clear? So now I can repeat this whole process for this j pi. So this becomes r pi plus gamma times r pi plus gamma square times j pi. So then r pi plus gamma times r pi plus gamma square times r pi, and so on, right? So you have an infinite sequence of 1 gamma, gamma square, gamma cube. So if you sum that, you are going to get 1 by 1 minus gamma r pi. Is that clear? Now, There is also another simpler argument given in the notes. I'm not going to do that now. Okay, so it's a simple symmetry argument to compute the same value. Okay, I encourage you to go and read it. Okay, now, so what are the implications here, right? Like, we're almost done. So what are the implications here, right? The implication is the discounting parameter gamma has no like control, like no part to play in the problem formulation. Okay, so which means you can remove this and do the average reward setting, like when you're in function approximation. Also, in practice, like you will rarely see people using average reward formulation. Okay, now this message does not mean that you should not use gamma for continuing tasks. Okay, you can use gamma for continuing tasks, but however, when you have settings like this, like infinite setting, like where like you have function approximation and like all the states are similar and so on, right? Like there is a lot of similarity between the states and so on. So then gamma becomes more of a solution component than the problem component. Is it clear? That this is a very subtle difference, which you can often ignore, but that is something good to know. Okay. Now, so the root cause. Okay. So first of all, why should we think about it, right? Like, so why can't we just do discounted control, and like with function approximation, right? Like, so the problem is once you go to function approximation, okay, if you remember in the tabular case, we had policy improvement theorem, right? Policy improvement theorem said that if you compute discounted returns and you do all your updates based on discounted returns, you are guaranteed to improve your policy in every time step, right? So that was policy improvement theorem. Now, the moment you jump to function approximation, it could be linear or non-linear, okay? Your policy improvement theorem doesn't hold, fine? So we don't have any guarantee that the policy will improve, which is an unfortunate result, but that is a trade-off. So if you want function approximation, you lose policy improvement theorem, okay? Now, there is another question with which I want to, like a quick note with which I want to stop, because that's the point for the next week's lecture. So the question is, can we actually develop function approximation methods where we have some guarantee that things would improve, right? So can we have a function approximation version of policy improvement theorem? So next week, we are going to talk about new class of reinforcement learning algorithms, like policy gradient methods, okay? Now, policy gradient methods, unlike all the value-based methods that we have seen so far, they won't estimate the values of the states or state actions. They will directly estimate the policy, okay? Now, in such a policy gradient approach, like we have what we will see next week as policy gradient theorem, which kind of guarantees that you are moving in the right direction. Okay, so this is for next week. So we will stop here, and I will take questions. If you have any questions, you can ask now, like, or we can stop. And this is my office hour. So if you have questions about your project, or if you want to talk to me about anything, like, you can come talk to me.